design of this AB in the left. Now, if and hello students, welcome to my YouTube channel VRacademy. We are discussing various topics of digital electronics. Today's topic of discussion is T flip-flop. We have already completed SR flip-flop, D flip-flop and JK flip-flop in the previous videos. Today we'll be going for T flip-flop. Now we'll be discussing about what exactly T flip-flop is, how to go for its design, and then we'll try to understand its operation. Depending on the operation, we'll have the truth table design, then characteristic table, equation, excitation table, and state diagram. So we'll discuss about each one of them in detail. First of all, we'll try to learn about what exactly T flip-flop is. So T flip-flop is nothing but T stands for toggle. So it is a toggle flip-flop. We have already discussed JK flip-flop, in which when J was equals to 1, K was equals to 1, at that time we were getting the toggle state. So in toggle state, T flip-flop directly it is termed as toggle flip-flop. Now we'll go for its design. So basically, when we are going for the design of T flip-flop, it is designed with the help of JK flip-flop. I have already said you that the basic element that you have to know in order to understand all the kinds of flip-flop or design of all the kind of flip-flop is SR flip-flop. Now, with the help of SR flip-flop, we are able to know about JK flip-flop. And once we are knowing about the JK flip-flop, we'll be able to know about the T flip-flop. Now, with the help of JK flip-flop, we'll be designing T flip-flop. But the question is, how we'll be designing it? So, it will be designed with the help of JK flip-flop by just joining the J and K terminal directly. I mean, if we are joining this is the J, this was, if I'll not have this line, this terminal is J, this terminal is K. So if we are joining J and K directly with a line, we'll be able to form and making that or representing that as T, then that flip-flop will become T flip-flop, and it is also known as toggle flip-flop. Now coming to its operation. In the previous videos, we have gone for writing the Boolean expression, and then we have gone for understanding the operation of those flip-flops with the help of those Boolean expression. But in case of toggle flip-flop, will not be able to do that. The reason being, once you are finding out that if there is a feedback system connected from the input to the output, then in that case what happens, if you are writing the Boolean expression, Boolean expression will not be dynamic in nature. I mean to say, basically when we are discussing about Boolean expression, it is a static expression. Static expression means that any change occurring in the output cannot be you cannot have that impression at the input. So for that reason, what we are doing, we are going for the explanation of this T flip-flop with the help of normal, you can say normal method. Okay. Now once again, I want to bring to your notice that while going for the previous flip-flop explanation, we were using the Boolean expression, and therein, in many of the places, I have used Q equals to something and Q bar equals to something in the Boolean expression. That was a slight mistake. You should be making it as Q plus and Q bar plus. The other expression, I mean the Boolean expression for that is absolutely fine, no issues with that. But the only change that you will be making in the previous flip-flops, that is SR, JK or D, you should be thinking Q as nothing but Q plus. I mean, wherever you will be finding out Q in LHS, consider that as Q plus and Q bar as Q bar plus. Okay, this is the only change. Now coming to T flip-flop explanation. Now we'll try to understand it, how exactly the operation occurs. So in order to understand that, what I will do, I'll just take the condition, and depending on the condition, we'll try to learn how exactly the things are going on. So for that, what I will do, I will just consider the previous input as, or you can say the storage input of Q equals to 0 and Q bar equals to 1. This is the first consideration we'll have, and depending on this, we'll try to learn what exactly happening and how we are deciding about the outputs. Okay, so let us go for that. The first thing is, I am considering this line as X, means output of this NAND gate as X and output of this NAND gate as Y. Now initially we have considered that the output, or you can say the data that is stored, is nothing but 0. So if this is 0, definitely this is going to be 1. Now coming to T. Now if we are having only one input, there are two possibilities. T can be either equals to 0 or it can be equals to 1. Depending on that, we are deciding the two cases. The first case is case 1, that is T equals to 0, and the other case is T equals to 1. Okay. Now Considering the first case, definitely we know that from the previous videos, until and unless clock does not becomes high, we are not able to start the operation. The reason being that if clock will be equals to 0, then it will have an impact of not starting the operation of this whole circuit. So that is why we are going for clock equals to 1 as the case. For every type of operation, you should be keeping the value of clock equals to 1. Now this is 1, this t is 0, and we know that this connection has come from here, so that value of q bar is equal to 1. So I am considering this as 1, this is 0, and this one is 1. Now we know that this is NAND gate, so if it is 1 0 1, the output of NAND gate is going to become 1. Okay. Similarly, if you are thinking about this as 1, t equals to 0, and this value is also equals to 0, so y will also come out to be 1. Now this is 1, this one is also 1. Now let us suppose this is the another input that is being connected, so you can have 1 from this side. When we are going for a NANDing of 1 and 1, it will definitely produce same output, that is 0. And whenever this 0 will be going to this place, you will have 1 0. The NAND of 1 0 is once again going to become 1. So we can say that if we are previously considering q equals to 0 and q bar equals to 1, after operation also q comes out to be 0 and q bar comes out to be 1. Similarly, you can have a proof. You can take this as 1, this as 0. You will be getting same 1 value and 0 value. So after getting this value, we can easily say or easily state that when t is equals to 1 and clock is equals to 1, we can say that the output q and q bar will not change, and that is why I am deciding that as last state, or you can say it as no change condition. I mean, there is no change that is occurring in case of t flip flop if we are considering that as input as 0. Now next condition is to consider t equals to 1. So now if I am considering t equals to 1, so we'll have 1 1 1. NANDing of 1 and 1 and 1 will give you 0. Similarly, this 1 is going to this place, but 1 1 0 will have the same impact and it will produce 1 as the output for the t equals to 1 value also. Now bring that 1 over here. So 1 0, the NAND of 1 0 is going to become 1. Similarly, this 1 will come out to this place, so you will have NANDing of 1 and 1 equals to 0. So you can see that after having operation of previous case as q equals to 0 and q bar equals to 1, when we are keeping the value of t equals to 1 and clock equals to 1, at that time the output comes out to be just the reverse. Q comes out to be 1 and q bar comes out to be 0. Q comes out to be 1 and q bar comes out to be 0. That means we can say that whatever input that whatever output that is being stored inside it, it is just getting complemented, or it is just getting toggled. So therefore, this condition is described as toggled state. This condition is described as toggled state. Now from here we are able to go for the truth table. When t is equals to 0, no change. When t is equals to 1, toggle. Now having this condition written in the form of truth table, we know that we can go for clock, t, q, q bar comments. So if clock is down, clock is down means whatever the value of t is, whatever the storage value is, the operation will not start. That is why I am telling this condition as no operation. Once clock becomes high and t becomes 0, whatever output that was stored previously, the same will come as the output. I have proven it over here. So that means it is last state, or you can say it as no change state. And the last one, if t equals to 1, we are getting the complement of previous state as the output. Therefore, that is called as toggle. Okay. Now, after having this, we'll be moving to the characteristics table. Now, we know that what is characteristics table? In this, the definition of characteristic table is that it is a table consisting of present state, input with their respective output, which is nothing but next state. So, first we'll consider these two as the input, qn and t. If two inputs are there, 4 combinations possible: 00 11 01 01. And using that one, we have to go for qn plus 1. If you can recall from the previous classes, qn plus 1 was written with the help of this comment line. So if t is equals to 0, you see, if t is equals to 0, what is the output? What is the comment line? No change. So if I'm t equals to 0, whatever the previous state is, the next state will have the same state, no change. If t is equals to 1, what is the state? Complement of last state or toggle. So 1, what is the complement of this last state? That is equals to 1. So we are getting 1 over here. Now after getting 1, once again t equals to 0 means last state is having 1, so we are writing 1. If it is t equals to 1, complement of last state, complement of 1 is 0. So I have written like this one. So this is about the characteristics table. Now coming to the characteristic equation, depending on characteristics table, we are designing the characteristic equation, which is nothing but a two variable k map. If we are designing a two variable k map, for the output qn plus 1, we'll be getting the answer. So one side of the what you can say matrix, I have written qn, other side is t, qn bar t, qn t, t bar, sorry, t bar t. After that, just go for 0 1 1 0 0 1 1 0. Now you can see that there is no condition of pair or quad or octet anything. So therefore we are just writing the expression. This is qn bar t plus qn t bar, which is nothing but qn XOR t. Now once we have got this, we'll be moving to the excitation table. What is excitation table? Excitation table is a table where we are having present state and next state as considered as your excitation, and from there we are deriving the response, that is input. We are finding out the value of inputs. So input is t, we are finding out t. Now if there are two variables, how many combinations are possible? 4 combination, 0 0 1 1 0 1 0 1. Now once you are done with this, you can see that I have written it previously also with the help of characteristics table. So you can see that if 0 0, present state 0, next state 0, at that time t is 0. So I have written it 0. 0 1, at that time t is 1. 0 1, at that time t is 1. 1 0, at that time t is 1. 1 1, at that time 0. That's it. Now coming to the state diagram, I have said you whenever we are going for the state diagram, it is the pictorial representation of state and its transition with the help of arrow. So if there is only one flip-flop, two states are possible. One is 0, the other one is 1. Now after that, if you are going for this 0th state and 1th state, taking the help of excitation table, 0 to 0, t is equals to 0. 0 to 0, t equals to 0. 0 to 1, t equals to 1. 0 to 1, t equals to 1. 1 to 0, 1 to 0, t equals to 1. And 1 to 1, that is t equals to 0. So this is the design. So I think you have understood the explanation. This is all about the t flip-flop, and after this we'll be moving to the next topic of discussion in the next class. If you have any doubt or any suggestion, you can come up with that. Your suggestions are highly appreciated. So if you have any doubt in understanding, you can write in the comment box. You can come up with your problem. I'll be giving you the solution of that one individually. Thank you for joining.